Hello everyone, welcome to Merrimack STEM Academy. Today we're going to talk about acid-base titrations. Understanding how acids and bases react is essential for understanding titrations. So, without further ado, let's get into it. Titrations are generally used to determine the concentration of an acid or base using an acid or base that we know the concentration of. There are a few different types of titrations. We can use a strong acid and a strong base, a strong acid and a weak base, or a weak acid and a strong base. The one titration that isn't used is weak acid and weak base. That's because the titration isn't really useful. The weak acids and weak bases don't fully dissociate, so the titration wouldn't go to completion. Let's look at an example titration. We're going to start simple, with a strong acid and a strong base. In this case, we don't know the concentration of hydrochloric acid, so we'll put a certain amount of hydrochloric acid in a flask. We're going to put 1 molar sodium hydroxide in a burette. During the titration, the sodium hydroxide will slowly be added to the flask. As we add sodium hydroxide, we will measure the pH of the solution. An indicator is often used to measure pH. Indicators change color at a certain pH. Phenolphthalein is a commonly used indicator you may have heard of. Since hydrochloric acid and sodium hydroxide are both strong acids and bases, they will dissociate completely, producing the hydronium ion and the hydroxide ion. These ions will react, forming water. This is a neutralization reaction. Let's make a graph based off this titration. On the x-axis is the volume of titrant, sodium hydroxide, added. The y-axis measures pH. The titration curve shows how the pH changes as we add sodium hydroxide. Before we add any sodium hydroxide, there is only hydrochloric acid in the flask. Hydrochloric acid is a strong acid, so the pH will be very low, around 1 or 2. The only ion present here is the hydrogen or hydronium ion. For simplicity, in this video I will be writing the hydrogen ion H+, but know that when the hydrogen ion reacts with water, it forms the hydronium ion H3O+. In the middle of the titration curve, there is a sharp increase in pH as the flask changes from acidic to basic. This middle point is called the equivalence point. Here, there are equimolar amounts of acid and base. Since there are equal amounts of acid and base, they will react completely, producing water. For a strong acid and a strong base, the pH equals 7 at the equivalence point. Beyond the equivalence point, we continue to add sodium hydroxide, but there is no acid left to react with the sodium hydroxide. The pH increases to around 13 because this is a strong base. At this point, the titration has gone to completion. How do we use a titration to determine the pH of hydrochloric acid? We can determine how many moles of sodium hydroxide we added to get to the equivalence point. Since the moles of acid must be the same as the moles of base, we can use this information to determine the molarity of hydrochloric acid. One important side note about this titration: in this case, the chloride and sodium ions are spectator ions. They do not affect pH, but they are present throughout the entire reaction. Let's look at a different type of titration, strong acid and weak base. The setup is similar. We have an unknown concentration of the weak base, ammonia, in the flask, and 1 molar hydrochloric acid in a burette. Although the setup is the same, the titration curve looks a little different. At the start of the titration, there is only ammonia. For weak bases, the pH will be lower than for strong bases. In this case, the pH is around 11. For titrations with a weak acid or weak base, there is a midpoint, or half equivalence point, halfway between the start of the titration and the equivalence point. At the midpoint, half the ammonia has reacted with hydrochloric acid. When hydrochloric acid reacts with ammonia, the ammonium ion is produced. Ammonium is a weak conjugate acid. If we make an ice table of this reaction, we can see that because half the ammonia reacts, the concentrations of ammonia and ammonium will be equal. When there are approximately equal amounts of a weak base and its conjugate acid, this is a buffer solution. So, the region around the midpoint is a buffer. Buffers resist pH change, so there is minimal pH change and a pretty flat curve in the buffer region. We can use the Henderson-Hasselbalch equation to determine the pH at the midpoint. The equation says that pH equals the pKa plus the log of the base divided by the acid. Since the concentration of ammonium equals the concentration of ammonia, we have pH equals pKa plus log of 1. Log 1 is 0, so at the midpoint, pH equals pKa. or pOH equals pKb. The ions present at the midpoint are ammonia and ammonium. At the equivalence point, hydrochloric acid and ammonia will react completely, producing ammonium. Ammonium is a weak acid, so it will partially dissociate to form ammonia and the hydrogen ion. The pH at the equivalence point is determined by the conjugate acid, ammonium. The pH at the equivalence point is so important, so let's talk about the equivalence point for the different types of titrations. For a strong acid and a strong base, the hydrogen and hydroxide ions will react to form water. This is a neutralization reaction, and the pH will equal 7. For any strong acid and weak base reaction, the strong acid and weak base will react to form the conjugate acid. The conjugate acid will partially dissociate, producing the weak base and the hydrogen ion. Because of this, the solution will be acidic and the pH will be less than 7. For a weak acid and a strong base, the opposite will happen. The weak acid and strong base will react to form the conjugate base. The conjugate base will partially dissociate, producing the weak acid and the hydroxide ion. Therefore, the pH will be greater than 7. Alright, now that you're a Titrations pro, let's see what you've learned. We're going to complete this chart to review what we've talked about. For the strong acid and strong base column, assume that we are titrating an unknown concentration of strong base with a strong acid. Okay, pause this video and see how much you can fill out. Let's start by drawing the titration curves. The starting and ending pH of the titration is determined by the strength of the acid or base. Weak acids and bases will have a pH closer to 7, strong acids will have a pH of around 1, and strong bases will have a pH of around 12 or 13. The midpoint is when half the acid or base has reacted to form the conjugate acid or base. For weak acids and bases, the pH equals pKa. In a strong acid, strong base titration, the reaction will produce water, so the pH will be determined by the concentration of strong base remaining. At the equivalence point, we have equal moles of acid and base. For a strong acid, strong base titration, the acid and base will react completely to form water, giving us a pH of 7. For a weak acid and strong base, the reaction will produce a weak conjugate base, meaning the pH will be greater than 7. Similarly, for a strong acid and weak base, a weak conjugate acid will be produced, and the pH will be less than 7. Now let's go through what ions are present. For this strong acid, weak base titration, at the midpoint, the strong base remains. For the weak acid, strong base titration, some weak acid remains, and some weak acid has reacted with the strong base to form the weak conjugate base. It's the opposite for the strong acid, weak base titration. We have the weak base and its conjugate acid. At the equivalence point, there is a neutralization reaction of the strong acid and strong base to produce water. For the weak acid and strong base, at the equivalence point, the conjugate base is produced. The conjugate base will partially dissociate to form the weak acid and hydroxide ions. Similarly, for the strong acid and weak base, the conjugate acid is produced, and it can dissociate to form the weak base and the hydrogen ion. Now, at the end of the titration, when the titration has gone to completion, we only have the titrant left. For this strong acid, strong base titration, the strong base has been completely used up and only strong acid remains. The strong acid will dissociate to produce the hydrogen or hydronium ion. For the weak acid and strong base, only the strong base remains, dissociating to form the hydroxide ion. For the strong acid, weak base titration, we're left with the strong acid, which again dissociates to form the hydrogen or hydronium ion. What ions are always present throughout the titration? Our spectator ions. For example, if we used hydrochloric acid, the chloride ion will be present throughout the entire reaction. Usually, our spectator ions are soluble and don't affect pH. For example, the chloride ion, bromide ion, and sodium ion are common spectator ions in titrations. Thank you for listening. If you have any questions, please leave them in the comments and we will do our best to answer them. Is there a topic you want us to cover next? Let us know in the comments. And be sure to like and subscribe for more videos about biology, chemistry, and everything STEM related.